Hello, and welcome to Astronomy 100. In this segment, we're going to continue our exploration of how we categorize the stars. And in the previous segment, we talked about what was called the stellar classification sequence. And so let's get right to the slide. If you remember from the previous segment, we talked about how the stellar classification sequence involves a sequence of lettered categories, and each of these lettered categories describes the appearance of the spectrum of the star. And the strange nature of it is that they get shuffled into the lettered sequence that you see here, O, B, A, F, G, K, M. Remember that ultimately what we're referring to is the surface temperature of the star, and of course how that affects the appearance of the spectral lines. So O-type stars are the hottest, M-type stars are the coolest, and so when you go through the sequence, O, B, A, F, G, K, M, you're going from the hottest stars in our universe to the coolest stars. And every star in our universe will fit one of these 7 spectral types. Now, historically, astronomers had to make a bit of a modification to this, and so let's go to that idea here. It works very much like how people on Earth have a variety of blood types. If you think about it, everybody on Earth has a different blood type, but we all fit into certain categories. And so some people are type A, some people are type B, some people are type O. But when it comes to your blood type, there's one secondary feature that also determines your blood type, and it's called the Rh antibody factor. So some people are O positive, some people are O negative, some people are A positive, some people are A negative. Well, it's very analogous to that. When it comes to the stars, every star has a spectrum that's going to fit into one of these lettered categories. But when you look at all the stars of one category, it turns out that there are some slight variations. For instance, all stars of type O have some differences in the appearance of their spectra. All stars of type K have some differences in the appearance of their spectra. Even though they're in the spectral type category K, there are some slight differences. So what the astronomers did was they added a number to go with the letter. So the idea is there's a number from 0 to 9 that goes with each of the lettered categories. So you can have stars that are B0, you can have a star that's an A7, you can have a star that's an F1 or a G9, etc. But remember, the concept is still surface temperature. So the O, B, A, F, G, K, M sequence is the hottest surface stars, surface temperature, to the coolest surface temperature stars. But the number in the lettered category is also hottest to coolest. So O is the category that we're in, but 0 is the hottest of the O-type stars, and then 9 is the coolest of the O-type stars. B0 would be the hottest B-type star. B9 would be the coolest B-type star. What star would be one step cooler than a B9? Well, then you would go down to A0. So the hottest of all stars are O0, the coolest of all stars are M9. And as a reference, our sun fits into this as a G2. So the sun's spectrum puts it into surface temperature spectral type G, but then the slight variation of its features makes it specifically a G2. A star that is a G1 would be slightly hotter than the sun, and a star that is a G3 would be slightly cooler than the sun. So the sun is a spectral type G2. Now, when it comes to categorizing the stars, we have a way to now create all of these categories that every star in the universe will fit into. The next question is, what can we make of that? What information can we glean from that? So what we're going to do is try to put it all together into some usable form. And it has to do with a discovery that's related to the surface features of a star and various other things about the star that will help us understand how they relate to each other. So let me show you the idea by first going to a graph here. Let's imagine that we are describing humans. Every human on Earth has features that allow us to be put into categories. We have male and female, we have height, we have weight, hair color, shoe size, whatever. And so humans have physical descriptions that can put us into various categories. Well, let's say that we had a question that was, how does one category relate to a different one? In particular, let's go to the example here on the screen. What if we were curious if somebody's body weight was related to their height. In other words, how much you weigh is maybe related to how tall you are. Well, the way that we would find out is we would simply do a survey. We would ask, let's say, 100 people several questions. One question might be, are you male or female? The next question might be, what is your age? And then the last question would be, tell us your height, and then of course your weight. And so on the screen here, you can see an imaginary set of results. What we have are male and female, and you can see that it's ages 1 to 50. But what each square or each dot represents is the information of somebody's body weight versus their height. So an example is this person here has this body weight, and then of course has this height. Well, when we put all of this information together for our sample, all 100 people put together, what you'll notice is there is a correlation or a connection. Notice how all of the symbols for each of these people gathers together in a line that stretches from the bottom left and it kind of curves over and goes to the upper right. So what this says is that there is nobody on Earth that's down here that would weigh many, many pounds, hundreds of pounds, but would only be, let's say, 3 feet tall. It's just not physically possible. Nor is there anybody who would be 7 feet tall, but only weigh 10 pounds. It's just not physically possible. So every human has one physical feature that is connected to or related to a different physical feature. So the idea is, what if you knew only one thing about somebody, other than their gender? Let's say that you only knew that they were 6 feet tall, a male that is 6 feet tall. If you go all the way up to where 6 feet tall would be, and then what you can do is you can read over and you could read down and you could predict that somebody that is 6 feet tall has the body weight that is indicated by the graph. So people that are this tall weigh this amount. And so this graph now unlocks one additional piece of information that you wouldn't necessarily know. Somebody simply tells you how tall they are, and now you know two things because you know how tall they are and you know how much they weigh. So the idea is, if there are physical features that connect the features to other features of a human, are there physical features of a star that connects to another physical feature of a star? So early in the 20th century, there were some astronomers that started to look at all of the features of the stars, their masses, their sizes, their temperatures, all the details that describe the physical properties of a star. And they started to put all these things together. And what they discovered is that there is a similar graph that can tie together many different physical features. And the two astronomers that figured this out were not necessarily working together, but they both stumbled on this idea at roughly the same time, so we give them both credit. The astronomer that is on the left was a Danish astronomer. His name was Einar Hertzsprung. The guy on the right was a very famous American in his day. His name was Henry Norris Russell. And so Mr. Hertzsprung and Mr. Russell discovered that you can pull together all of the physical features of stars into one diagram that suddenly becomes very descriptive and very helpful. And in their honor, we refer to this as the Hertzsprung-Russell diagram, or in short, we call it the HR diagram. And that's what's here on the right, and we'll come back to this in just a minute and look at it in detail. But the key concepts that we're going to address are, how does this diagram link together all of these physical features of stars? What are the measurable properties of stars? And of course, what else can this diagram tell us that may not necessarily be so obvious on its surface? So let's look at a larger version of the HR diagram here. It does look very complicated, but let me try to break it down for you in a fairly easy way. On the diagram, what we have are 4 sides, and each side describes a physical property of a star. Across the top is the star's surface temperature. Across the bottom is the star's spectral type. The reason why they both go left to right is because the spectral type of a star is related to its surface temperature. So if a star is an O type, of course it's very hot, and if a star is an M type, then of course that star is relatively cool. So when you move left to right or right to left, you're changing spectral type, but remember, you're also changing surface temperature. The vertical axis says luminosity on this side, and then it says absolute magnitude on this side. The reason why they're both on the vertical axis is because when you change the luminosity of a star, or how much energy that it produces, it will also affect its absolute magnitude, which is defined as how bright it would look if it were a distance of 33 light years, something that we talked about in a previous segment. So moving vertically changes this property, moving horizontally changes this property. And so in this diagram, what you can see are many different stars. Each one of these black dots represents a star. They all have names. We've put in some examples for you, and of course here's the sun at this point right here. Why is the sun right here? Because the sun is a G2 spectral type. We just saw that. The sun has a certain surface temperature. The sun has a particular amount of energy that it produces, its luminosity, and the sun has a particular absolute magnitude. So notice one dot on this diagram pulls together 4 different physical features into one sort of a big picture. But there's more. Notice that the dots seem to be scattered a bit. There's 2 groups, one group right here, and there's another group right here. And then if you go down to the bottom, you can see there's a line, sort of a group of stars down here. And we will eventually come back to why that is. But if you think about tying together some of the properties we've talked about in previous segments, we can actually add 2 more things to the HR diagram. For instance, in a previous segment, we talked about how the size of a star, its radius, is proportional to the luminosity of the star and the temperature of the star. So R, L, and T are all related. Now you'll notice on the diagram, if I move vertically, I'm changing the value of L. And if I move horizontally on the diagram, I am changing the value of T. So everywhere on this diagram, there's a value of L, there's a value of T, and so therefore, everywhere on the diagram, there's a value for R. So let me put those in there. These green lines, a little tough to look at, but they're meant to stand out. These green lines represent a value of R that is the same all the way down the line. So an example is, everywhere along this green line, the value of L and the value of T combine to give you a value of R that is indicated in this diagram. So this line here, every one of these stars has the same size. Everything on this line has the same size. Everything on this line has the same size. Notice the number says 1/100th. So these stars are 1/100th the size of the sun. These stars are 1/10th the size of the sun. Notice this says 1 solar radius, so every one of these stars is the same as the sun, same size. These stars are 10 times bigger. These stars are 100 times bigger. These stars are 1,000 times bigger. So notice when we put the star Betelgeuse on the diagram, it not only tells us its energy, its absolute magnitude, its temperature, and spectral type, but it also tells us that Betelgeuse is almost 1,000 times bigger than our sun. We can actually figure that 5th piece of information by where it is on the diagram. Now, in addition to that, in a previous segment, we talked about what was called the mass-luminosity relationship. And if you recall, what that meant was a star's mass is related to the amount of energy that it produces. Stars that are more massive produce more energy. Stars that are less massive produce less energy. Notice that when I go vertically up and down on the diagram, I'm changing the value of L. So this is a large value of L up here. And then if I go all the way down here, this is a small value of L. So what that tells us is that when we look at the HR diagram, stars that are up here have very high luminosities and therefore are very massive, and stars that are down here have very low luminosities and therefore are not as massive. So you can now also tell the mass of the star based on where it is on the diagram. So notice there are 4 pieces of information plus the size of the star, and add to that the mass of the star. 6 pieces of information come from where the star is located on this diagram. So as you can see, the Hertzsprung-Russell diagram is able to pull together many of the different features of a star, the physical features of the star, into a way that makes us able to relate how those features are affected by other features, or how they all come together to give you the big picture of what a star is and all the details that go with it. What we'll eventually do is see how this information can lead us to a better understanding of how the star is formed, how it lives, and how it dies. But we'll save that for a future segment. I hope you'll join me.